the crust. And I want to be clear that the crust is adhered to on the underside of the lithosphere and is often considered part of the lithosphere, so it can get a little bit confusing. But for this class, we're going to delineate the crust as separate from the lithosphere, just so you can kind of keep those three zones with two components kind of clear in your mind. So again, to repeat, we've got an inner and outer core, which is number one, a mantle, which has an astenosphere and a lithosphere, that's number two, and the third one, which is the crust. And there's two types of crust, a continental crust and an ocean crust. So this is where the Earth's temperatures are the coolest, and it's the hardest part of our planet. So we've got lots of really solid matter up here, and I gave the analogy of like a brownie that has cooled over time, that the outer part of the brownie is the crustiest, the most solid, and every day that goes by, the outer part of the crust gets more and more hard, and that starts to get ridges in it and cracks and fissures in it. And that crust zone becomes thicker and thicker over time too, as the rest of the brownie starts to solidify as well. Our crust is a really small part of our planet. So when you think about how big mountains are, especially like the Himalayas and the Andes, even the Appalachians, and we think how magnificently large they are, those mountains added to all of the continents and all of the bottoms of the oceans only make up 0.01% of the total mass of the Earth. So it's just this tiny little veneer of the planet that we live on. So really small, roughly only at its maximum 44 miles thick. So we're going to talk about equilibrium lines in a few minutes. But with that thickness, half of that thickness is considered, sort of on the surface, and some of that thickness is then penetrating into the asthenosphere. So two types of crusts, we said there were, a continental crust and an ocean crust. And this is not a terribly good diagram for showing isostatic rebound, but it is really a good diagram for showing the ratio between how thick a continental crust is and how thick an ocean crust is, and where that lithosphere is relative to the asthenosphere. All right, and we've got a lower mantle here as well as part of the asthenosphere, but I just want you to concern yourself with this zone right up in here. So this lithosphere, we've just considered this MOHO, or it's short for Mohorovic discontinuity, which is the margin of contact between the lithosphere and the continental crust and the ocean crust and the lithosphere as well. So the continental crust is lighter and taller and higher, and it's got a lot more volume than the ocean crust. And that has everything to do with energy. We know that when something's full of energy, it's more voluminous. So our continental crust was a high energy environment. So it's going to have more volume to it than the ocean crust. There's more energy, but there's also different matter here. The continental crust is less dense than the ocean crust because of the matter that it's made up of. So of that material, the continental crust is mostly made up of granite. All right, there's other components I know. There are sandstones and mudstones and schists and gneiss and all sorts of rocks that are on the surface of the earth, but the vast majority is granite, all right? And all of the rocks, for the most part, have mostly, and in particular granite, have mostly silica, aluminum, and potassium with some cadmium and sodium in them. So these are light minerals. There are other minerals as well in this volume of matter, but the highest majority of matter is this light stuff. making the continental crust itself light, and light stuff rises above heavy stuff, right? So the ocean crust, on the other hand, is basalt. Basalt is also got some silica in it, and it needed silica because if it didn't have enough silica, it wouldn't sit here. It would sit down in here somewhere. So it has to have enough silica that it rides on top of the lithosphere. All right. So it's got silica for sure, but it's also got magnesium and iron in it. So much heavier material in higher proportions of those heavier materials than on the continental crust. And we know that iron and magnesium occur on the continental crusts as well, because that's where we've always mined them from. All right, so we've got to factor in buoyancy and how buoyant something is. So if something is nice and light, think like styrofoam, it's going to be more buoyant. So it's going to sit higher. And that makes this diagram a little bit better because we can see there's a higher volume of matter here and an equal proportion that is dipping into the lithosphere as well. So we've got a lot of matter that is above and below sort of this equilibrium line that is this imaginary line that runs halfway between the upper portion of the continental crust and the lower portion of the continental crust. So it's pretty buoyant and sits higher. The ocean crust also has an equilibrium line, and 50% of it sits below that line and 50% sits above that line. But because the ocean crust overall is more dense, it sits at a lower elevation than the continental crust. So we had mentioned isostasy as well. So what this means for isostasy is that we've got a less dense matter here, but we've got more matter, so it's going to sink further. So it's going to then sit below the ocean crust in terms of volume. And over time, as this matter either increases in volume, that means this is going to rise. That means this will also sink a little bit further. So there's always 50-50 ratio. This will also erode over time, and this matter is going to erode into this zone, this continental shelf right here. So rivers are going to bring matter and deposit it here. All this yellow stuff is considered the deposit by this illustration, and that's going to add mass out here, which means this is going to start to sink a little bit lower. So we are deflecting these locations with isostatic rebound. One more diagram on isostatic rebound just to show you that a little bit more fully. So I've got a continental crust here, which is more voluminous. And as time goes on, we're going to erode the top, which means we're going to isostatically lift this stuff up equal to the volume of matter which was eroded out here. So that's one way of lifting and re-eroding that matter. We also can see isostatic rebound happening on glacial masses, where when you add glaciers to a large landscape, they carry a lot of weight to them. That weight's going to depress the rock matter, the continental crust, a little bit. It's also going to then compress that lithosphere a little bit and then create a rebound on either side. So you can see there's some deflection up and deflection down here. When we lose this ice, and I authentically want you to use your imagination and imagine this as the Great Lakes, as we lose this mass, this is going to rebound back up. So where we have the Great Lakes now, was a thick part of the Laurentide ice sheet that penetrated deep into the asthenosphere. And so we're still currently rebounding back up, and eventually we're going to rebound up so high that we're going to lose the lakes.